Hello, thank you for watching this video. So in this video we're on bed action 10 and we're talking about tangents, right? Hopefully this lesson will be helpful on dealing with some Euclidean geometry problems. So let's get going. So the first thing that you need to understand is to know what a tangent is, right? So a tangent to a function, right? It is a straight line that touches a function exactly one point, right? But in this case, we are talking about tangents to circles. Are you with me?
Yes.
Fine. So a tangent to a circle is something like this. Let's suppose we have this circle over here. Can you see the circle? A tangent is a line, straight line, that will touch this circle at exactly that point. Are you with me? So here's a tangent. It touches exactly at that one point. So there's only one point at which your tangent touches. And it's exactly that one. Are you clear?
Yes.
No problem. Then there are a few things that I will say about tangents, but you should just know what it is. So the first thing that I have to say, if you have a circle, like this here and a tangent, and let's say this point O here is the center of the circle. The first theorem, or maybe one of the theorems that we will prove, is that if you join this center of yours to the point of contact between the tangent and the circle, which is that point over there, is the point of contact. We say that point, that line, which is your radius, because the line is from the center to the circumference, will be perpendicular to the tangent. So this is one of the theorems that we will prove in this session. I'm not sure if that makes sense. Does it make sense?
Yes.
So it's one of the theorems that we will prove in this class, that a radius is perpendicular to what? To a tangent at the point of contact. So before we do that, I want us to look at something, right? A theorem that I'll call theorem shortest distance. I'll start here first. By starting here, I'm trying to go to this theorem that I'm talking about. But I want to start with theorem shortest distance. Can you see?
Yes.
So, with this theorem, what I will say is, the shortest distance, right?
Yes.
Between a point and a line is a what? Is a perpendicular one. It's a perpendicular distance. Distance. Is it clear?
Yes.
I'm saying the shortest distance between a point and a line is a perpendicular distance. I'm saying if you have a line here and a point here, are you with me?
Yes.
The distance that will be shortest between this point and the line is the one that is perpendicular to the line. Anything else is not the shortest distance. Do you understand?
Yes.
Is it clear?
Yes.
No problem. So, I'll call this line, maybe just line. And point, let's say this point is A, and this one is B. So, what I'm trying to prove here is that AB is the shortest distance. Are you with me?
Yes.
Okay, no problem. So let's say proof. So to prove this, that AB is the shortest distance, I'm going to use our method, favorite method, proof by contradiction, right? So we're going to assume that this statement is false, right?
Yes.
And then we try to work with some mathematical knowledge that we know, right? And we'll run into some problems. And I said that if you assume that your statement is false and you run into some problems, that is equivalent. So assuming that statement is false and running into some problems or contradictions, that is equivalent to your original statement that you want to prove. So we'll assume that this statement is false and try to do maths with it, or try to use some geometry knowledge that we know about geometry so far. And then if we run into problems, then that would mean that our assumption was false and therefore our theorem is true. So let's go. So we'll use profile contradiction. So we'll say, okay, suppose, let's assume that this theorem, shortest distance is what? Is false. I'm not sure if you understand what I'm going to say. We're assuming that the theorem shortest distance is false. If theorem shortest distance is false, what does it mean? It means that we do have a shortest distance between a point and the line, but that distance is not perpendicular. Do you understand? Because we said the shortest distance between a point and the line is the perpendicular one. So we're falsifying the statement. To falsify it, your shortest distance, you should have a shortest distance between a point and the line, but it should not be the perpendicular one. So in that case, AB is not the perpendicular distance. That's what this thing is saying. I'm not sure if you understand what I'm trying to say.
Yes.
Which means, by saying this statement is false, AB is not the shortest distance. So, what does this mean? That means AB is not the shortest distance. Are you with me?
Yes.
If AB is not the shortest distance, there should be another point somewhere on the line. That will give us the shortest distance. But there should be a closest point to A that lies on the line. So let's call that point C. So let C be a point on the line such that AC is the shortest distance. So it doesn't matter if it's on the left or the right of B. So since AB is not the shortest distance, what does it mean? It means there is a point C, right, on AB on the line, so that AC is the what? Is the shortest distance. Are you with me? So let's go there and plot our point. Let's say our point may be somewhere here, C. So let's point C. There is C. So AC is our shortest distance because we assume that this one is not. And then if AB is not, there should be a point. Then we'll say C is that point. But if you look at this, we have a right angle triangle. So in that case, you know very well that if you have a right angle triangle, it's this triangle here. You can say your AC squared, right?
Yes.
Is equal to what? It's called AB squared plus BC squared. Why? This is Pythagoras. I'm not sure if this makes sense. So look, to get the square of AC, you must add the squares of both of these sides. Because this is a triangle, right? This is a non-degenerate triangle, which is a real triangle. It's a normal triangle. So in order to get AC, which means this side of yours, you must add the squares of both of these sides. What does that tell you? It tells you that both of them, each one of them is less than AC.
Yes.
Do you understand?
Yes.
If I need to add the squares of both of them, which is the square of this one its own, is less than
Yes.
that of AC.
Yes.
Which is the square of AC is greater than that of AB.
Yes.
Do you agree?
Yes.
So, what that means that your AC squared is greater than AB squared. Right?
Yes.
Therefore, your AC is greater than what? AB. Do you understand?
Yes.
But this doesn't make sense because we said AC is the shortest distance. But if your AC now is greater than AB, that is a contradiction. This is a problem. It goes against our assumption that AC is the shortest distance. Because if AC is the shortest distance, this one should be smaller than that.
Yes.
Actually, AC should be smaller than AB.
Yes.
But look what we have there. We have that AB is less than AC, which is a contradiction to our assumption. Because we said AC is the shortest distance. from the line. But now we're finding out that AC is not the shortest distance. AB is. So this is a contradiction, right? This is a problem. This is, from what we are doing, this is impossible from what we said initially. Because we said AC is the shortest distance from the line. But now we're finding that AB is the shortest distance. So it goes against what we assumed or what we deduced up there. Therefore, where is the problem? Where did the problem start? The problem started here, which is our supposition was false, right? Which is our supposition that theorem shortest distance was false. It was itself false. Therefore, the theorem shortest distance is true. Do you understand? So we can say, therefore, our supposition, which is this supposition, is what? Is false. And therefore, theorem shortest distance is true. What does that mean? It means that the shortest distance between a point and a line is a what? Is a perpendicular distance. I'm not sure if this does make sense. So this point, if you have a point in the line and you are asked to find the shortest distance, you should always know that the shortest distance is the perpendicular distance. I'm not sure if you hear what I'm trying to say. Okay, so now we're going to start with theorem 7a, right? I think I've laid a foundation for it, at least, to be able to prove it with no problems. So, theorem 7a is telling us that a tangent to a circle is perpendicular to the radius at its point of contact, right? So, if we have Tn as a tangent, right, and your Tn is a tangent at A here, and you join OA here, this is the point of contact of the tangent in the circle. This is the point of tangents. This is where the tangents is happening. Are you with me? They are saying this radius of yours, ON, of course, O is the center. This radius, ON, is perpendicular to the tangent. Do you understand? So what we have here, we have a circle with center O, and we have a tangent Tn, and this tangent is touching the circle at point A then. If you join the radius OA, they are saying this radius of yours, OA, will be perpendicular to the tangent Tn. That's why I placed that navy blue thing there, so that this is what we want to prove. We want to prove that perpendicularness of the tangent and the radius. That's what we're trying to prove. No problem. So how are we going to prove this? To prove this, we're going to use a similar method as above. Not as above, actually. It's going to be different. We're going to say, okay, we're told that A is the point of tangency. This is the only point where the circle touches the circle, right? All other points on the left-hand side and on the right-hand side are outside of the circle. Do you agree? All other points, which is a point here, you will have to draw outside of this point here. Even there, it doesn't matter how close it is, it will always be outside because that is the only point where they are touching. Do you understand? Okay, so we're going to say, okay, proof, and have constructions for our proof. Construction. Are you with me?
Yes.
To do this, I'll say let's mark point B and C on the left and right of A respectively. So let's place the point B and C on this line Tn, so that on the left, one is on the left and the other one is on the right. Are you happy with that? Let me extend this line. Maybe we have N here in T there. So we're going to have B maybe somewhere here on the left, right, and C maybe somewhere there. Are you with me? So the next thing that we're going to do as part of our construction, let's join OB and OC, right? So that these lines intersect the circle, right? So that these lines, which is these two lines, your OB and OC, intersect the circle at where? At maybe point E and at point D and E somewhere there, right? At point D and E respectively. Are you with me? So what are we going to do? We're going to join OB. Can you see OB and OC over there? So that they intersect the circle at point D and point E respectively. Do you agree? Is it clear so far? No problem. So what we're going to do, you can see that your OD is called OA, is called OC. So your OA is called OB, is called OC. Do you agree?
Yes.
What is the reason for this? These are radii. So all these three guys, this from here to here and this from there and all to there, they are all equal. OE, sorry, it can't be O, should be OD, sorry. It should be OA. OA is equal to OD, right? Because that's what it is, and it's called OE. All those are radii. Are you with me? And then the next thing that we need to do, we need to express OB now. Let's write down OB. OB is made up of OD and DB. Do you agree?
Yes.
So, from our diagram, you can see that your OB is called what? Called OD plus DB. This is from your diagram, right? Diagram. Are you with me? Do you agree with me when I say now? The same OB, right, is equal to your OD. Your OD is this radius, which is the same as OA here, plus DB.
Is that OB?
OB is called OD, right, plus DB. Do you agree with that?
Yes.
But this is called OA.
Yes.
So which means your OB is called OA plus the small portion over there.
Yes.
Do you agree?
Yes.
Now, if you do this, you will quickly see that it's clear that your OB as a whole is smaller than OA.
Yes.
Actually, it's greater than OA.
Yes, it's greater.
Your OB is greater than OA.
Yes.
So it's greater than OA. Because OB is called OA plus something. So once you add something on your OA, another distance, then it should be greater than OA. Do you agree?
Yes.
So, which means by this, since your OB is on the left of A, do you see this?
Yes.
Your OB is on the left hand side of A. What that means is that your OA is smaller than all the distances that are on the left of A.
OA.
Yeah, the distance OA is smaller than all the distances that are on the left hand side of A.
Yes.
Because whatever that you draw, it will always pass the circle. So it will be OA plus whatever.
Yes.
Do you agree? So in this case, we can say, okay, therefore, your OA is less than OB. Do you agree with that? You can do the same thing with OC and say, look, our OC is equal to what? Called OE
C.
plus
EC.
EC. This is from a diagram. Do you agree?
Yes.
Then, but OE and OA are the same.
Yes.
Which means your OC is equal to what? It's equal to OA plus EC.
Yes.
Which means that your OC should be bigger than your OA, because your OC is OA plus something else, right? So if we want to conclude this, we can say, okay, therefore your OA is less than OC. What does this tell us? Your OA is smaller than all the distance that are, your OA is less than OB. It means that this distance here is smaller than all the distance on the left hand side. Which is, if you take n, so this is the shortest distance from the left hand side. Do you understand? And your OC, your OA is also smaller than all the distance that are on the right hand side. Do you understand? So if your OA is smaller than all the distance on the left hand side, and your OB, same OA is less than all the distance on the right hand side, it means OA is the shortest distance from that point over there. So OA is the shortest distance on this line TA, on this line TN, because your OA is smaller than all the distance on the left hand side and all of the distance that are on the right hand side. By the theorem that we just proved, we proved that the shortest distance between the point and the line is what? Is the shortest distance. So in this case, we see that OA is the shortest distance on the line. They should be perpendicular. Does it make sense? Okay. So in that case, we can say, therefore, OA is perpendicular to what? To TN. What is the reason? Because OA is the shortest distance between point O and line TN. Not sure if this makes sense. So we have shown here that OA is the shortest distance, right? Between that point and this line TN. They should be perpendicular distance. That's how we did it. Does it make sense? So what I'm going to do now, I'm going to prove the converse of this thing, which is I'm going to the other direction now. So what does it mean? If I have a line, right, such that the angle between the line, which is not necessarily a tangent, because I'm saying to you here, a tangent, the angle between a line is perpendicular to a radius. So a tangent is perpendicular to the radius. That's what I was saying here. Are you with me? So on the converse, I'm saying that if I have a line such that that line is perpendicular to the radius at the circumference, then that line should be a tangent.
Yes.
That's what the converse says. Because here I said that I was telling you that a tangent would be perpendicular to the radius at the point of contact, which is at the circumference. Right? So right now I'm telling you that if you see a line such that that line of yours is perpendicular to the radius at the circumference, then that line should be a tangent. That's what I want to prove. So let's go. So we're done with this one, right? So we're going to go to theorem 7b. Are you with me?
Yes.
So what am I saying? I'm saying a line perpendicular to a radius, right? At the circumference of a circle. Are you with me?
Yes.
A line perpendicular to the radius in the circumference of a circle is a what? Is a tangent. So we have a line such that this line is perpendicular to the circumference of a circle. So it's perpendicular to the radius at the circumference. So you have a situation like this. So here's your center here. Can you see center O? And you have this line here. so that this line of yours is perpendicular. Can you see? Then I'm saying that this line should be a tangent. Does it make sense?
Yes.
Do you understand it?
Yes.
Okay. So, in this case, we're going to prove this. What are we going to say first? This is a proof, right? Let's suppose that our theorem, the statement is false. I'm going to use the perfect contradiction as well, because you don't need to know the proof, but I'm just showing you. So, let's suppose that our theorem 7b is what? Is false. Are you with me?
Yes.
Are you following me?
Yes.
Then, if theorem 7b is false, what does it mean? It means we have a line perpendicular to the radius. And that line of ours is not a tangent, as you can see here. So, we have this kind of situation here. Because this thing is not a tangent. Is it a tangent?
No.
It's not a tangent because it's cutting this circle twice.
Yes.
It's not touching it. Crossing it, touching it, intersecting it twice. So, not a tangent. So, if you're supposing that theorem 7b is false, we have this kind of situation where you have a line that is not a tangent, but it's perpendicular to your radius. Are you with me? No problem. Then, your construction. Let's construct here. Construction. So let's say this point is A, maybe here, and this point is what? Is B. For your construction, it's just going to join what? OB.
Yes.
Do you agree?
Yes.
So that you have a triangle. Do you agree with me?
Yes.
So, let's join OB. Can you see?
Yes.
So, in triangle what? AOB. In triangle AOB. You can say that OA is equal to Y. These are radii. So, these two are equal. What does it say about angle A and angle B? Therefore, angle A is equal to angle B. And they're both what? 90 degrees. So, if you say angle A plus angle B plus angle O, what do they give us? They give us 180 degrees because these are sum of angles. Sum angles of a triangle, right? In that case, we have 90 plus angle O is equal to 180 degrees. Therefore, the angle O is equal to 0 degrees. This is impossible because this is a triangle. This is a problem. So, this is what? This is impossible. Because we have a triangle. So, how can we have a triangle? And how can we have a triangle and have this angle here being 0? This is not possible. This is a contradiction to our knowledge. That in a triangle, none of the angles is 0 degrees. Unless this angle is not there, which means it's only this thing, this OB is exactly sitting over OA, which is we have just a tangent meeting once there. So, in that case, we have a contradiction, which means our supposition, which is this, is false. Because the one that we assume that this is false, it gave us problems. So, assuming that it is false and getting those problems is equivalent to the statement that we wanted to prove in the first place.
Yes.
Are you with me? Yes. So, therefore, which is it? What I was saying? Which is therefore our supposition is false and theorem 7b is true. Are you with me? So what does this mean in short? It means that if you want to prove that a line is a tangent to a circle, you must prove that the angle between that line and the radius is 90 degrees. That's one way of proving that a line is a tangent. You must prove that the angle between a tangent, you must prove the angle between the line of interest and the tangent is a what? is 90 degrees. That's what we are proving, that a line is a tangent. We know, we've proved that a tangent is perpendicular to the radius at the point of contact, which is at the circumference, right? Also, we just proved that if a line is perpendicular to a radius, then that line should be, if a line is perpendicular to the radius of the circle at the circumference, then that line of interest should be a tangent. So I'm done with theorem 7a and 7b. You should know this. Not the theorem, not the proof necessarily, but the theorems behind them. Then I'm going to go to theorem 8. I'm going to clean the board and then we do theorem 8. Sure? Okay, so now we're doing theorem 8, right?
Yes.
At theorem 8, you are given a circle here, right?
Yes.
And two tangents, tangent AB and tangent AC, right?
Yes.
Those two tangents are drawn from the same external point. Do you know what external means? External means outside. So this point is outside of this circle. So if you have two tangents, right, which is tangent AB and tangent AC, that are drawn from the same external point, which is these points. AB is a tangent to this circle, and AC is a tangent to this circle, right? So both of them are drawn from that point. Are you with me?
Yes.
So they are drawn from the same outside point or from the same external point. I'm not sure if you understand what I'm trying to say. Then those tangents will be equal in length, which means the part between the point and the point of tangency, and this part from that point and the point of tangency, these two will be equal. I'm not sure if you understand what I'm trying to say. I'm trying to say to you, your AB, if AB and AC are tangents, this part AB and this part AC are going to be equal. Do you understand what I'm trying to say? Which means if I can join BC maybe like this, then ABC should be an isosceles triangle.
Yes.
Because this and this will be equal. So those angles will be equal angles opposite equal sides.
Yes.
That's what I'm trying to say. So I'm saying two tangents that are drawn from the same external point are equal in length. So which means the part from the point, common point, to the point of tangency, and the point from the external point to the point of tangency to tangent P, these two lengths should be equal. So let's go and prove that. So proof. Are you with me?
Yes.
Start by construction. Can you see?
Yes.
So what are we going to do? We're going to join what? OB and OC. Can you see?
Yes.
So we're going to join OB and OC. Here they are. You need to know this proof. Can you see?
Yes.
Okay. What next? And then join what? Let's join OA. Are you with me?
Yes.
Let's join OA, which is it. Or maybe let me use the navy color. This was supposed to be straight, sorry. Can you see?
Yes.
It's OA. So you are looking at two triangles. Triangle ABO and triangle ACO. So what we need to do now, we need to prove that these two triangles are congruent. If they are congruent, these two sides are going to be equal because those are corresponding sides of these congruent triangles. Are you with me?
Yes.
So let's prove that they are congruent. So okay. In triangle what? In triangle ABO. Are you with me?
Yes.
And triangle ACO. I can say if this is 1 and 2 and this is 1 and 2, I can say B1 is equal to 90 degrees. Why? From the theorem 7a.
Yes.
Because we said the radius is perpendicular to what? To a tangent. You can say the same thing about C1 as well. It's equal to 90 degrees. Why? Because the radius is perpendicular to what? To a tangent. Are you with me? Are you following me?
Yes.
Okay. Therefore, if you look at this, your angle B1 is equal to angle C1 is equal to 90 degrees from this They're both equal. They're both 90. No problem. And then we can say your OB is equal to OC. Why? These are radii. Are you with me?
Yes.
These are radii. And then
OA.
your OA is equal to OE. Why? This is a common side. They are both sharing this side. So these two triangles are congruent. By what? By the right angle that you have here and there, by hypotenuse and by common side, by equal side. So we can say, therefore, triangle what? ABO is congruent to what? To triangle ACO by right angle, hypotenuse, and the corresponding sides. In that case, therefore, your AB, can see AB is equal to AC. Why? These are corresponding sides of congruent triangles. So I prove that these two things are equal. So if I can draw and make triangle ABC, you will see that these two, you will have an isosceles triangle here. Because those two will be angles opposite equal sides.
Yes.
And I'm done with this proof. This theorem. I'm going to move on to theorem 9, which is the Tan-Chord theorem. Is this theorem clear? Do you have any questions for me?
No.
So what I'm going to do, I'm going to clean the board and we're going to go to theorem 9, which is the Tan-Chord theorem. And it's converse. And we'll do exercises after that and we'll be done with this question. All good. Let's go to Tan-Chord. So let me clean the board. Okay, so now we're going to do theorem 9a, right?
Yes.
They call it the Tan-Chord theorem or alternate angle theorem. So this theorem states that if you have a tangent, right? Let's say you have a tangent here. Let me just maybe draw a different diagram. If let's say you have a circle and a tangent to a circle. Are you with me?
Yes.
Are you with me?
Yes.
And then this is the point where the tangent is happening. This is the point of contact between the circle and the tangent. If you have a chord that is drawn from this point here, are you with me? If you have a chord drawn from this point here, and this chord of yours subtend an angle on the other segment. Because you can see a chord splits your circle into two segments. This segment, which is the major segment, and the minor segment. Are you with me? So we have a tangent, this, and it touches there. And you draw a tangent here from this point, which is this one, and that one as well. Maybe. So what they're saying that the angle subtended by the chord that is drawn from this point of chord, or from this point of contact, this, which is this angle subtended by this chord, will be equal to this angle over here. Does it make sense?
Yes.
They're saying an angle between a tangent, which is this tangent over here, and the chord that is drawn from this point of contact, which is this chord here, will be equal to the angle that is subtended by the same chord but on the other segment, not this segment which forms an angle with the chord. Because you can see there's this segment over here,
Yes.
and part of this segment forms an angle with this tangent.
Yes.
So this angle here would be equal to the angle that is subtended by the same chord on the other segment. In a similar way, let's say you look here at this angle over here. This is a tangent, right?
Yes.
And this is the point of contact.
Yes.
You draw, let's say suppose that you drew another chord which is here.
Yes.
You can see that there's an angle here.
Yes.
So the angle between your tangent and the chord which is drawn from the point of contact
Yes.
will be equal to the angle that's subtended by that chord on the other segment.
Yes.
So that's what alternate means. It means on the other segment. So which means this angle over here will be equal to that angle over there. That's what this theorem says. Does it make sense?
Yes.
So in this case, we have three cases. This angle here will be equal to that angle over there.
Yes.
This angle here will be equal to that angle over there.
Yes.
This angle here will be equal to this angle here. This angle, this angle TAC
Yes.
will be equal to angle B.
Yes.
And this angle NAB is equal to angle C.
Yes.
which is the same thing here as well. But just here, I just combined the two. So here, at case 1, what is the difference between this and this? The difference is that this angle and this angle are both acute angles. They're both less than 90. That's the only difference. You can see these are less than 90, both of them. That one, you can see this angle here, TAC, is an obtuse angle. Right? So in this case, it's more like, I can say, a case 1. Let's say you can say you have an acute case. If that makes sense.
Okay.
So in this case here, case 2, you have an obtuse case. Because this is an obtuse angle. So, want to show that it works on acute angles, it works on obtuse angles. Even if they are both combined, it will still work. This is the combo. What do we call it? Let's say maybe combo case. Combo case. Yeah, because I've combined the acute angle, or maybe acute angle and that one over there. Okay. So this is a combo case. So we're going to prove that this angle here, which is this angle here, you see this angle, case acute A is equal to this angle over here. So if this acute one will work, so will that one, because it will be the exact same proof. And there's only for us to prove an acute case there. We'll just focus on the obtuse one. That we don't know, because an acute will be dealt with in the same way. Are you with me? Yes. So let's go with the acute case. Let me clean the board and we do the acute case. We're doing what? The acute case, right? Say acute case. So, what can we say on that acute case of ours? So, sorry? Actually, let's just say proof first. I'll use the red ink. Say proof. I'm dealing with the acute case. Are you happy? No problem. So, I'll start with the construction first. Construction. I need you to know these things. So, first thing that we're going to do, we're going to draw a what? A diameter. What is the name of our diameter? It's AOD. Are you with me? So O is the center. Like this one. So draw AOD. Is D here? Let's say O is somewhere here. Are you with me? Yes. After joining AOD, we join BD. Right? Let's say we join what? BD. So here's BD over here. Are you happy with this? Yes. So, you can say we have A1 here, do you agree? And we have A2 here as well. So you have B1, maybe B2 here as well. Do you agree?
We have A1, A2.
A1 and A2, B1 and B2.
A3.
There's no need.
Okay.
There's no need. What is A1 plus A2?
Oh, A1 plus A2, 90.
A1 plus A2 is equal to 90 degrees. Why? Because this is a tangent. And you can see that OA is a what? It's a radius. So it should be 90. If you have A1 and A2, you're looking for the entire angle here, which is the angle between the radius and the tangent. So that should be 90 degrees. What are you going to say here? You're going to say it your reasoning. Your tangent is perpendicular to what? To radius. That's why that is 90 degrees. Are you with me? Yes. What is B1 plus B2?
B1
Uh-huh.
plus B2.
B1 plus B2. What is the answer to that?
Oh, it's 90.
It's 90 degrees.
Yes.
Why? These are angles subtended by diameter.
Yes.
So angle in
Semicircle.
semicircle. That's subtended by diameter.
Yes.
So 90 is equal to 90. So which is A1 plus A2 should be called B1 plus B2. So we can say, okay, since these two, the right hand sides of these two are equal, so are the left hand sides. So it's A1 plus A2 equal to B1 plus B2. Right? No problem. But look at B1 and look at A2. Let's look at A2 and look at B2 and look at A2. They are both subtended by the same arc DC.
Yes.
So we can say, okay, your A2 is equal to B2. These are angles in the same segment.
Yes.
Are you with me?
Yes.
In that case, for A2, for B2, you can put A1 as well.
Yes.
So your A1 plus A2 is equal to B1 plus A2. Because they're equal.
Yes.
So this and that go away.
Yes.
Therefore, your A1 is equal to
B1 is part of B1.
B1. Which is what we're trying to prove to begin with, which is this angle. We're trying to say that this angle over here is equal to that angle over there. Are you clear?
Yes.
Is it clear? Now, let's go to obtuse case. We're going to what? Obtuse case. So, let's go for the obtuse case. It's okay. We have obtuse. So we're done with this one. Oh, not really. Obtuse case. Here is it. So for the obtuse case, it's the same thing. We're doing the same construction. Are you with me? What are we saying? I'm going to say draw what? Diameter. What? A, we're here now.
Yes.
A,
No, B.
A, O, D. Right?
Yes.
We draw this diameter. What else? And then we join BC or BD, BD, sorry. Draw BD. Like we did there. So, in this case, we're going to draw a diameter AOB. AOD. Here's a D here. And maybe here's an O somewhere here. And then we join BD. Are you with me?
Yes.
Are you following me? So we're trying to show that this angle over here is equal to that angle over there. Are you still with me?
Yes.
Fine. What do we have now? Okay. We have angle what? Angle 1. Do you agree?
Yes.
Yeah. And this angle 2. Do you follow?
Yes.
And then we're going to say this is angle B1, this angle B2. Are you following me?
Yes.
What is angle O1?
O1 is 90 degrees.
90 degrees. So your angle O1 is called 90 degrees, right?
Yes.
Why? Because a tangent is perpendicular to radius.
Yes.
Are you with me?
Yes.
Because you see OA is a radius.
Yes.
Fine. What is B1 plus B2? It's called 90 degrees as well. Because this is a diameter. So, which one? Not B1, B2. So your B1 is equal to 90 degrees because only B1 is subtended by the diameter. What are you going to say? Angle in semicircle. Are you following me? Fine. Let's leave that. And look at the angles that we haven't talked about. Look at A1 and A2. Your angle A1, your angle A2. Why do I say O? It can't be O. It should be A here. Right? Should be A1 that has 90
Yes,
degrees.
it's A1.
Yeah. So angle A2 is equal to angle B2. Are you with me?
Yes.
Or maybe I can say, therefore, since these are both equal to 90, your A1 is equal to B1. Do you see?
Yes.
Are you clear?
Yes.
In a similar way, I can say, okay, what is it? I can say A2 is equal to B2.
B2.
These are angle in same segment. Then, if I can add these, my A1 plus A2 should be the same as B1 plus B2. Because if this is equal to this and this is equal to this, so if I add them, they should all be the same. Are you following me? Are you sure? Okay. But then, look, A1, this and this are equal. That's what we said, right? What did we say? We said, wait.
Is that A1?
Oh, actually, we said this is equal to this. A1 and A2. You see that A1 and A2 is TAC. Do you see that? Which is TAC is equal to B1 and B2, which is just angle B. Angle B. Which is what we wanted to prove. Which means this angle, this entire angle out here, A1 and A2 is equal to B1 and B2. I'm not sure if that does make sense. Do you want me to do the combo case?
Yes.
Or is it straightforward? Yeah?
We can do it.
Okay. Because at here, you're going to do the exact same constructions.
Yes.
And then at the end, you're just going to combine them. Or maybe let me do it. You never know. Let me do it. I'm going to clean the acute case and the obtuse case. But it's all going to be what I've just done, but I'm just going to combine them. Okay, so now we're going to do the combo case, right? We'll be doing the combo case, which is this one. So, you do the same stuff that you did above. Are you with me? So, this is the construction. We'll draw a diameter first. It will be AOE, because the last alphabet is D here. So it's going to be AOE. Are you with me? Yes. Then the next thing we're going to join DB. So you draw a diameter AOE. Here's a diameter. Maybe the E is somewhere here. And then you draw BE. Should be BE. Should be BE. Are you following me?
Yes.
So let's say maybe here, you have your 1 and 2. Do you agree?
Yes.
And say, let's say you have 1 here, and this is 2, and this is 3. Do you agree?
Yes.
So A1 plus A2 plus A3, what do they give you?
A1
Plus A2 plus A3. They give you 90. So your A1 plus A2 plus A3, they'll give you 90 degrees. Why? Because your radius is perpendicular to what? To a tangent. Are you following me?
Yes.
What is your B1 plus B2? They give you 90 degrees. Why? Sorry? Angle in a semicircle. Angle in semicircle. So if these two are both equal to 90, which is they are both equal to each other, which means your A1 plus your A2 plus your A3 is equal to your B1 plus your B2. Are you with me?
Yes.
But look at this. Your B2 and B3 are equal.
Wait. B2.
Your B2 and your A3. Sorry, your B2 and your A3.
Oh, okay.
They are both separated by the same arc EC. These are angles in the same segment.
Yes.
So, B2 is equal to A3. And they're both equal, why? Angles in same segment. These are angles in the same segment.
Yes.
So in that case, what do? We can just, where we see B2, we can put the B3, B2, A3, right?
Yes. Yes.
So your A1 plus your A2 plus your A3 is equal to B1 plus A3. So this and that go away. So you get that your A1 plus your A2 is equal to B1, which is your A1 plus A2 is this angle here, NCAN. Can you see? Therefore, your CAN is equal to that angle here, which is angle B. Are you with me?
Yes.
Which is this. Can you see this?
Yes.
Straightforward.
Straight.
Happy?
Yes.
No problem. Now, we're combining these two. What is B1 plus angle D?
B1.
Plus angle D.
Okay. B1
Mm-hmm.
and angle D
Mm-hmm.
at 180.
B1 plus angle D is equal to 180 degrees. Why? These are opposite angles of a cyclic quadrilateral. Quad. Are you happy with that?
Yes.
What would I get if I were to add? If I were to add TAC, did you say angle A? Angle A, TAC plus A2 plus A1. If I was to say TAC, right, plus A2 plus A1, what did I get? TAC is this angle here, TAC is this angle here, and you add A2 and A3.
Oh, it's 180.
You get 180.
Yes.
So you get 180 degrees. What is the reason?
Angles on a straight.
These are angles on
In a straight line.
a straight line. Are you with me?
Yes.
No problem. So which is this 8 and 8 are the same.
Yes.
Which is this side is called that side.
Yes.
So your B1 plus angle D is equal to your TAC, right?
Yes.
Plus A1 plus A2. Do we agree?
Yes.
Are you with me?
Yes.
But then, look, we said your B1, what is it? Is it the same B1?
Yes.
Is equal to CAN. Or your CAN is called, what is CAN? CAN is this,
Yes.
right? Is your A1 and H is called to CAN. Do you agree?
Yes.
So, which means this and this are equal.
Yes.
From what we proved,
Yes.
you can say B1 is equal to A1 plus A2, and they're both equal to CAN. Is that true?
Yes.
We proved this. We proved this above. So, which means on the base of B1, I can just say CAN plus angle D plus T is equal to TAC plus CAN. So this and that will go our way. Therefore, the angle D is equal to TAC. Right? Let's go and check it. Angle D, which is this angle here, called TAC, which is true.
Yes.
That's the combo. And we're done here. So, this theorem was saying that if you have a tangent to a circle at a certain point, and from that same point you draw a chord, and that chord of yours subtend an angle in the alternate segment, which is in the other segment, right? The angle between the tangent and the chord will be called the angle that is subtended by the chord on the other segment. That's what this theorem says. Are you following?
Yes.
So, I'm going to do the converse. We do examples, and we're done here. Are you still here?
Yes.
Do you want me to do the converse?
Yes.
We're going to do theorem 9b. I'll clean the board now. Okay, so now we're done with theorem 9a, which is a Tan-Chord theorem. We're going to do the converse of it. So you still remember that theorem 9a was telling us that an angle between the tangent and the chord at the point of contact, right, is equal to the angle subtended by the same chord in the other segment or in the alternate segment. Right? So it was telling you that if this is a tangent here, let's say Ln is a tangent, this angle here between the tangent and the chord will be equal to the angle that's subtended by the same chord on the other side. And the angle this side, if this is a tangent, the angle between the tangent and this chord is equal to the angle in the alternate segment. Are you following? Then, now, what are we doing now? In this case, this is the converse. We're told that we have a line Ln, right? And we're told that this line, the angle between this line Ln and the chord AC, maybe, is equal to the angle in the alternate segment. So we have a line Ln. No one says a tangent. You can see it's not even a tangent. It's crossing twice. So we have a line Ln. Are you with me? And the angle between your line Ln and the tangent and the chord, and the chord at the point of contact, because your line Ln is crossing, is intersecting the circle at the end point of that chord AC. So that's telling you that the angle between the line Ln and the chord AC is equal to the angle in the alternate segment. The claim is that if you have this kind of situation, this line Ln should be a tangent. Are you following? So let's try to read it. That's like a line intersecting the end point of a chord, making an angle equal to an angle subtended by same chord in the alternate segment is a tangent. Do you understand? A line intersecting an end point of a chord, making an angle equal to an angle that is subtended by the same chord in the alternate segment is a tangent. So which means, if you have a situation like this where a line intersects a chord at its end point, such that the angle between the line of interest and the chord is equal to the angle subtended by the same chord on the other segment, then that line should be a tangent. You can see that I didn't draw a tangent. I made sure that it cuts twice. So we're about to prove that this should be a tangent. So let's go and say proof. Are you still with me?
Yes.
Okay. Then I'm going to say construction. Are you with me? Construction. So I'm going to draw a what? A diameter. What? AOD. So I'll draw a diameter AOD. Can you see?
Yes.
Here's AOD here. Then what? I'm going to join what? BD. So I'm going to join BD. So let me just remove the x's, right?
Yes.
We know that these two are equal, right?
Yes.
Let's say this is B1 and A1, B2 and A2. Are you with me?
Yes.
So we're told that these two are equal. That's what the statement is telling us. So in that case, I'm going to say B1. Actually, what is B1 plus B2?
It's 90.
It's called 90 degrees. Why? Angle in
Same.
semicircle. Right?
Yes.
Then, what is A1 plus A2?
It's 90.
Equal to 90 degrees. Why?
90 is given. Oh.
We don't have that.
Yes, we don't have that.
We don't know. We can't say this is 90 degrees.
Yes.
Are you with me?
Yes.
We can't say this is
90.
90 degrees. Fine. But we know that this is 90 degrees.
Yes.
Okay. But we know that A1 is equal to B1. We're given this thing.
Given. Yes.
Are you with me?
Yes.
And I'll say A2 is equal to B2. These are angles in same
Awesome.
segment. Do you agree?
Yes.
So if you add these two, you find that your A1 plus A2 is equal to B1 plus B2. But what is B1 plus B2? 90. Therefore, your A1 plus A2 is equal to 90 degrees. We said on theorem 2b, if the angle between a line and the radius at the point of contact is 90 degrees, then that line is a what? It's a tangent. If, we said in theorem 2.7b, if the angle between a radius and the line intersecting your radius at the point of contact is 90 degrees, then that line is a tangent. Therefore, Ln is a tangent. Why? Because a line perpendicular to what? A radius. Or done here. Does it make sense?
Yes, it does.
Also, if you wanted, you could have used maybe proof by contradiction, or maybe you like this one better.
I like this one.
Okay. Also, you can look. You can see after drawing this, you can say let's draw a tangent at A, right?
Yes.
Here's a tangent at A. You know that this angle here is equal to this angle here.
Yes.
But this is a problem. How can this small angle equal to this and that big one equal to this? This is a contradiction. Do you see?
Yes.
Because look, if you're saying you're drawing a tangent here, you have two angles, you have this angle here, and you have that angle over there. Can you see?
Yes.
You know that by Tan-Chord, this one will be equal to this.
Yes.
But this one you already given that is equal to the entire angle. So this is equal to this. So how can these two angles be equal? This is a problem. Also, now that you know tangents, I want to remind you of a theorem that says that if you, I'm done with this, and I'm just talking now. So that you said the opposite angles of a cyclic quad are supplementary.
Yes.
Do you remember that?
Yes.
Another way of proving it, you can say, okay, I have this thing over here, this cyclic quadrilateral. Can you see it?
Yes.
Are you with me?
Yes.
Let's call it A, B, C, and D. You want to prove that B plus D is equal to 180 degrees. Are you with me?
Yes.
To do this, first thing that you do, let's draw a tangent here at C. Are you with me? Are you following me? Let's draw a tangent here at C like this. And join these two things here. Are you following me?
Yes.
Are you following me?
Yes.
Then, look at this angle over here. This angle here, let's call it maybe C1, I don't know, all of it. And this one, I'll call it C2. AC is a chord. Do you agree?
Yes.
AC is a chord. So, which means this angle is equal to C1, this one.
Yes.
And this one is equal to C2.
Yes.
So, you say what? C1 is equal to angle D.
C1 is called angle D.
Why? This is a Tan-Chord.
Yes.
And you say your C2
C2
is equal to angle
angle B.
B. Why?
Yes, Tan-Chord.
Equal to?
Oh.
Yeah, still Tan-Chord as well.
Tan-Chord.
Are you with me?
Yes.
But what is C1 plus C2? C1 plus C2 is equal to
180.
B. No, B, you are right.
Oh,
You can say angle D plus angle B. Are you with me? But C1,
you said C1
If this is equal to this, and this is equal to this plus this, equal to this plus this.
Okay, okay.
So you C1 plus C2 is equal to 180 degrees.
Yes.
These are angles on
Straight line.
a straight line. Are you following me?
Yes.
But these two are equal to that. So which is angle D plus angle B is equal to 180 degrees.
This is it.
Yeah.
Oh,
You can also prove it this way.
okay. We're just drawing the tangent.
So draw a tangent there
Okay,
and label the entire thing
okay,
as C1, maybe this one is C2.
okay.
If you want to prove that these two are equal to 180 degrees, draw a tangent down here or up there,
Okay.
and then join these two. So you can see that you have a D1 and a D2. So look. So this angle here, wait, or this, you have a tangent down here. So this angle between the tangent, this angle here, right, is equal to this angle down up here.
Yes.
And this one here is called the angle up there, this one. Do you see? It's doing the same thing but different side.
Okay.
And that's it. So you can, I think that is the easier one for me.
Yeah, this one is straightforward.
So I'm going to
Right.
clean the board. We'll do examples and we'll be done. Or you think you don't need examples?
I think I can do them by myself.
So we want to stop here.
Yes.
Okay. Then guess we're done for the day. I'm tired too. I've been talking for more than an hour now. And I hope it makes sense to you as it does to all of us. So this is it. There are no examples for this one. Thank you for watching. Cheers.